Hello, my name is Melanie Finch and I'm from Monash University in the School of Earth, Atmosphere and Environment. Today I want to tell you about some work that I've done on the ephemeral development of C' shear bands in ductile shear zones. This work was dominantly done when I was at the University of Tübingen in Germany on an Alexander von Humboldt Foundation postdoctoral fellowship. And but now I'm back, at Monash University in Australia. Prior to this work that I did in Germany, I worked quite a bit in naturally deformed rocks, in naturally deformed shear zones. So this is a thin section image in cross-polarized light that's from a rock in one of the shear zones that I've studied, and the outcrop that this is from looks like this. So this is an orthogneiss from the Zanskar shear zone in the northwest Himalaya. And you can see that this rock has light and dark bands. So there's quartzo-feldspathic layers here, and then these darker layers here. And you can imagine that these two layers deform quite differently to each other because they comprise of different minerals, and different minerals have different strengths. So they deform quite differently to each other. We can see a number of different shear sense indicators in this outcrop. So we have C planes in this orientation, S planes in this orientation. And then of course we have my favorite, the C' shear bands that dip down in the direction of shear. So in this case, it's top down shearing, normal shearing in this outcrop. So if we have a look at the thin section again from this outcrop, you'll again see this compositional banding into light and dark bands. So the lighter bands are quartzo-feldspathic up the top here, and the darker bands are these layers that are rich in biotite and muscovite. So within this layer down here, the main features are these really fine-grained biotite, which has accommodated a lot of the deformations, really ductily deformed. And then we have these mica grains, these muscovite grains with the really high birefringence, the pink and green birefringence colours, and they form mica fish. And then in the top bit here, you can see that the quartzo-feldspathic layers have deformed quite differently. So there's a lot of recrystallization in areas where there's dominantly quartz, so there, down here, for example. But the feldspar, the big feldspar porphyry class, are deforming quite differently to everything else. So they undergo brittle fracture, and then the pieces are sheared apart. So this part here, 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 and here all would have been one grain originally, and it's been sheared apart during that ductile deformation. So different minerals have different responses to the imposed stress. If we have a look at the structures in the bottom layer down here, we can see that there are C planes in this orientation through here, sort of forming the top of those mica fish as well in that orientation. And then we have S planes, which dip in this orientation here, giving us that asymmetry and that, the shear sense that's indicated here to top to the right in this case. And we also have C' shear bands, which have this orientation through here. So they dip down in the direction of shear. And you can see that these have developed in the layer that's rich in biotite, but not in the quartzo-feldspathic region. So we're already starting to understand something about how these C' shear bands form just by looking at what minerals they form within. So it's really the biotite that is defining those C' shear bands, and which is the weakest mineral within this rock. And that's something we see reflected in previous literature as well. So C' shear bands are also called extensional crenulation cleavage. So if you've read about those in the literature, I'm talking about the same thing here. So we understand pretty well how SC fabric forms. We've known that for a while, but C prime shear bands have definitely been more enigmatic. So the way we understand that SC fabric forms is that we start off with a shear zone that has a shear zone boundary. That's what's indicated here. And S-planes nucleate at 45 degrees from the shear zone boundary. And I'll show you this happening a bit later on in the models. And then these S-planes rotate towards parallelism with the shear zone boundary until they form C-planes. And all the while we have new S-planes nucleating at 45 degrees from the shear zone boundary and rotating towards parallelism with the shear zone boundary. So that can form a structure that looks schematically like this, and you can see that reflected in this rock, the thin section image over here. But yeah, so we kind of get that, but we do not really understand how this forms, how these sorts of structures form. Although we've had, there's been quite a few studies that have tried to understand this. I just want to mention at this point that if you'd like to read more about this work that I'm going to describe today, then I've published these results in this paper here with this great team of people here who are all experts in sort of L modelling. And yes, so you can find that paper in the Journal of Structural Geology, or you can also find an unformatted copy, an author copy on ResearchGate, or you can email me to get that and I'll send it to you. Or you can find all the movies and this paper on my website, which is melaniefinch.net. So you can check that out there. Yep. Okay, so previous research has suggested that these C prime shear bands nucleate on the plane of maximum shear strain rate. Other papers have found that they form due to flow parallel to the shortening eigenvector due to bulk hardening, or perhaps due to general shear. So that's quite a common conception, that you need general shear, so pure shear and simple shear, to form these C prime shear bands. And it's also been suggested that they form during the last stage of shear zone activity. So these studies have focused mainly on naturally deformed rocks. And this last idea in particular has been suggested in part because C prime shear bands often seem to cross-cut or displace S-planes or SC planes. So it does seem from those cross-cutting relationships that they form last. So that's one idea as well. Experimental studies have also been done that look at this question of how C prime shear bands develop. And these studies have focused on the strength ratio between phases, between different minerals, and the proportion of weak phase. So these two factors are thought to be important in the development of C prime shear bands. So these studies have found that C prime shear bands form when the strength ratio between phases is at least 3 to 5. So that's the weakest mineral. So in this case, the biotite here is at least 3 to 5 times weaker than the hardest phase, like feldspar. And they also found that you need at least 20% of the weak phase, which is biotite in these examples, to nucleate these C prime shear bands. So these experimental studies start off with, this is a quartzite, so they can start off with a microstructure like this or a microstructure like this. That's the starting material. And they deform the rocks in particular deformation apparatus, and then they end up with something that looks like this. And so they've got those C prime shear bands there. So by changing the temperature and the imposed stress, perhaps the strain rate, so by changing the factors, the variables in the experiment, they're able to simulate different strength ratios that way. So what I've done is something that looks quite similar to this, but from a numerical modelling approach. So I use the numerical modelling platform L, and you can find out more about L here at this website. And I had to start off with a starting microstructure like this. So you can see it looks quite similar to the quartzite in the previous slide, but it's not a quartzite. I have 3 different phases that each have different strengths, and I'll get to that in a moment. So the way that L is set up is that we have these grains, which we call flins, and flins are sort of defined by these boundary nodes that are linked with straight segments to form polygons, and that's what a grain is. And then behind all of this, we have this network of unconnected nodes, which are called U nodes, and they store information about strain rate and stress, which is super handy. So you can find out what's happening at every point in the model during deformation, which is the really cool thing about this technique. So what we do is we have this starting microstructure and we deform it 1 step. So it looks like this. I'm working under simple shear. You can also use pure shear in L, but I'm doing simple shear. So yeah, deform it 1 step, and material that leaves the bounding box here reappears over here. So we get these wrapping boundaries. We use full field viscoplastic deformation code, and you can find out more about that from the paper if you're interested in the specifics of that. In L, the deformation is accommodated by dislocation glide on crystallographic slip systems. So this is trying to simulate the way that minerals deform in a naturally deformed rock. So every mineral within this rock would have a different set of slip systems. So biotite has different slip systems to feldspar, for example, and each of the slip systems within each of these minerals has a certain resistance to shear. So this is known as the critical resolve shear stress, the resistance to shear of a particular slip system. So yeah, there are a number of slip systems in each mineral, and we simulate that in L by giving our phases, our minerals, a number of different slip systems and setting those at different strengths or different resistance, critical resolve shear stresses. So we had 3 phases: a strong phase, which is supposed to be, sort of simulates the most important aspects of feldspar, of how feldspar deforms. We have an intermediate strength phase, quartz, and we have a weak phase, which is supposed to, it's sort of like mica. It simulates the way that mica deforms in these models. So they are grey, white, and black respectively, but you don't have to worry, I remind you of that when we look at the movies. We had 2 different variables. So we had 3 phase strength contrast levels, and then we had 4 weak phase proportions. So 2 different variables that were manipulated there. So that gave us 12 conditions overall. The phase strength contrast conditions were low, medium, and high. And this was just manipulating the difference in strength between the weak phase, the intermediate phase, and the strong phase. So in the low phase strength contrast condition, the intermediate phase was 1.5 times the strength of the weak phase. In the medium phase strength contrast condition, it was 2.5 times, and in high, it was 4 times. And then the strong phase was always double the strength of the intermediate strength phase. We also varied the proportion of weak phase. So we had 5, 15, 30, and 45% weak phase. And we wanted to see what the effect of that was. In all conditions, the weak phase had a basal plane that was weaker than its non-basal planes. And this was to simulate the most important aspect of how mica deforms, which is it has this really weak basal plane there. So yeah, we had these 12 conditions in total. I simulated dextral simple shear in 900 steps, and each step involved a gamma change of 0.02, so an increase in the finite strain with each step. So you can see this microstructure. This is, the progressive development of the microstructure over 18 steps, and you can see, that you're starting to change the shape of those grains. So this is at step 18, but we went all the way up to step 900. So now I'm going to show you the results, the movies from from the work. And in each of these, I'm going to have the condition at the top here, so 5% weak phase and a high phase strength contrast, and what that means. So the intermediate phase is 4 times the strength of the weak phase, the strong phase is 8 times the strength of the weak phase. And here's a reminder of which phase is which. So black is the weak phase, grey is the strong phase. And then over here, so this is the grain microstructure, and over here we've got the strain rate at the same step. And you'll see that red is the highest strain rate and blue is the lowest strain rate. So I'll talk you through these movies as they deform. So the first thing that happens is that the weak phase aligns to the S plane and then quickly rotates over into parallelism with the C plane. So pretty early on, we're forming that SC fabric. In layers of weak phase that are parallel to the shear zone boundary, we see the highest strain rate. So the highest strain rate is in these C parallel layers through like this. We start to see the development of C prime shear bands. You get a hint of it through there. So they dip down in the direction of shear. And what you'll see as we go along is that they're always defined by these layers of weak phase. The layers of weak phase gradually connect up to form these through-going shear planes like this. So the way they do that is that there's really high stress at the tips of these weak phase layers, and that high stress sort of effectively pushes out the other minerals, the intermediate strength phase and the strong phase, until those weak layers of weak phase can sort of connect up and form these through-going shear planes. So this area here would be really high stress as this layer tries to connect up. We're seeing, so there's an asymmetrical fold that's formed, and that actually formed in response to the development of a C prime shear band. So there's another C prime shear band here, and what we see is these C prime shear bands experience sort of 2 different fates, depending, well, on a few different things, but so they can undergo shortening and collapse, and sort of that means that they thicken and form these sort of weird thick layers of biotite, or they can rotate back into parallelism with the C plane. So just then you saw there was something going this direction, and now it's rotated backwards into parallelism with the C plane. Here, this is rotating forwards, and then it looks like it's shortening, so the layer's getting thicker, and that's the end of the simulation. So you can see through here we have a number of different asymmetrical folds, and if you want to watch this movie again, you can through those methods that I described earlier, and you'll see that these asymmetrical folds form, and then they get sheared apart and form these rootless isoclinal folds that are so common in shear zones everywhere. So this modelling also provides an insight into how those particular structures form as well. So not too many C prime shear bands in that model, but you'll see that they increase in proportion with a high proportion of weak phase. So moving on now to 15% weak phase and a medium phase strength contrast. The beginning of this movie is the same as in the previous movie. So the weak phase aligns to the S plane and then quickly rotates over into parallelism with the C plane. The strain rate is highest where the weak phase is parallel to the C plane, so really high there. And we start to see C prime shear bands, and these form through the rotation forwards of these, or the forward rotation rather, of these layers of weak phase. So layers of weak phase join up and then begin to rotate forwards, like you can see here. That's rotating forwards, and then it looks like it is shortening internally and sort of collapsing, forming that thickened layer there. So another C prime shear band through here, and that was also undergoing shortening, and parts of it have rotated back into parallelism with the C plane. So two main fates for C prime shear bands, and I'll talk more about that later. The development of C prime shear bands is sort of difficult to see in this moving image, but the great thing about L is that you get, a snapshot at every step, so you're able to move through those quite slowly and actually really identify or correlate changes in strain rate, changes in stress with the development of these C prime shear bands. So that's what I did. Here we've got a through-going shear plane defined by a continuous layer of weak phase. And you can see that once that develops, there's not much that happens in the rest of the model. This is really partitioning all of the strain rate. But yeah, we do see some rotation of layers down here. So there's a C prime shear band there, but it's not rotating backwards because the rest of the model isn't really deforming very much at this point in time, because the strain rate is all accommodated by this shear plane here. Moving on now to the 30% weak phase model. At the start here, you can see there are these vertical regions, layers of weak phase actually, that accommodate sort of a higher strain rate. You couldn't see them too well there, but they're a feature in the next model as well, and I'm going to point that out. They're more pronounced in the next model, and they are C double prime shear bands. So they form antithetic to the sense of shear rather than synthetic like C prime shear bands, and they only seem to be a major feature early in the early stages of the development of these models, unless there's a high proportion of weak phase. So more on that in a moment. So we see C prime shear bands forming in this model as well, but the high proportion of weak phase means that we form more of this anastomosing sort of network of interconnected weak phase. So that's sort of heading more towards that sort of structure where the weak phase is forming that sort of network. We still see the development, of this SC fabric. Between the different models and the different phase strength contrasts, there are differences in the deformation of the strong phase and the intermediate strength phase as well. So, the strong phase is able to retain its equant shape when there is a high proportion of weak phase. And when there's a higher phase strength contrast, sort of makes intuitive sense there. Here you can see the development of an isoclinal fold that formed near, so one of these patches of weak phase. So these patches of weak phase form when C prime shear bands like this one sort of shorten internally and then form that sort of structure. So sometimes these form these X-shaped structures, which we also see in naturally deformed shear zones, but have been thought to form in a sort of due to different mechanisms compared to this. So here you can see the shortening of this C prime shear band has caused folding in the layers of strong and intermediate strength phase on either side. So that's a major way of forming these isoclinal folds in these rocks. A high proportion of weak phase means that it's harder to form those interconnected, it takes longer to form those interconnected layers of weak phase and for them to partition the strain. So we actually see that the strain's more distributed when there's a high proportion of weak phase. Here we have 45% weak phase, and you see those vertically oriented shear bands, which are the C double prime shear bands, through like this. It's a good one down here. You can see this is a rotating lithon of strong and intermediate strength phase, and the rotation on this is accommodated by the antithetic shear planes on either side, which are defined by weak phase through like that. So in this model, the higher proportion of weak phase means that the strong phase can retain a more equant shape to higher finite strains. We also see the development of C prime shear bands within this model, but they are more ephemeral, so don't stick around for as long. Things tend to rotate forwards and rotate backwards quicker than what they do in the other models. You still sort of see some of these C double prime shear bands in this model as well. They're pretty short-lived though. In this model, even though, so there's a high proportion of weak phase, and those weak phase layers are trying to connect up, trying to form these through-going shear planes in the model, but because the strain rate or the strain is sort of distributed more over the whole model, it takes a little bit longer for that to happen. So so C prime shear band through there. So really an anastomosing shear zone network that's formed here through that high proportion of weak phase. We still see asymmetrical folds developing in this as a result of shortening on either side, so above and below layers of weak phase that are deforming at a higher strain rate than the surrounding phases. Okay, a lot of rotation in these models as well, as those layers of weak phase sort of accommodate that deformation, that rotation. So even though there is a high proportion of weak phase, it does form a through-going shear zone in the end, but yeah, it would be relatively short-lived because there's lots of other places that strain can localize here as well. Okay, so there are two main processes that actually form the C prime shear bands, and the first one that I want to talk about is that when there's high stress in a hard phase bridge. So what I mean by this is when we have a situation where we have these distinct layers of weak phase and they are sort of trying to connect up. So the high strain rate in these layers means that these areas here and here, so in there and there, they are at high stress. So that high stress sort of pushes those intervening minerals of strong phase and intermediate strength phase out of the way, and it allows these layers to sort of connect up and eventually form a through-going shear zone. So that's the ultimate fate of these sorts of things. But in the meantime, there's quite a heterogeneous distribution of strain rate within these layers, and the formation of C prime shear bands is partially in response to this. So here we have this layer here that's deforming at a high strain rate. The minerals above, the phases above of strong phase and intermediate strength phase are forming these asymmetric folds. So this area here is shortening, and that causes other areas of the model to undergo rotation. So this layer up here rotates forward to accommodate shortening in this region through here, and that causes the development of a C prime shear band. That C prime shear band rotates forwards, and then in this model rotates backwards again. So that forward rotation and then backward rotation back into parallelism with a C plane. So this is what we mean by C prime shear bands being ephemeral. They rotate forwards, then rotate backwards. The second process that seems to form C prime shear bands is a strain rate increase. So here we have a layer of weak phase, and there's one segment of that layer of weak phase that has a high strain rate, and the other parts of that layer are at a lower strain rate. Those regions that are at a high strain rate are sort of, you can think of it, they're kind of moving faster than the layer sort of in between them. And so to accommodate that higher strain rate there, this layer actually needs to rotate forwards. So it rotates forwards and forms a C prime shear band like you see there. And then when the strain rate decreases, then the C prime shear band rotates backwards back into parallelism with the C plane. So again, we see that these C prime shear bands are ephemeral in this during this process as well. Okay, so we find that C prime shear bands do not form when there's 5% weak phase and a low phase strength contrast. So I didn't show that particular movie, but we find that no C prime shear bands form then, but they do form in all the other models. So it seems like you only need 5% weak phase to form them, as long as the phase strength contrast is a bit higher than in this low phase strength contrast condition. They're more common when there's a high phase strength contrast, but they're also more ephemeral. So things rotate forwards and backwards more faster in this model. So C prime shear bands rotate backwards and become C planes, and I've shown a few examples of this, or they undergo shortening and collapse. So I referred to this a bit when we were watching the movies. So we have a C prime shear band here, and that can shorten and collapse and form sort of these X sort of shaped structures like this. And then when these form, the layers on either side need to fold to accommodate that shortening, and they do that. Contrary to previous studies, we do find that C prime shear bands do not nucleate on the plane of maximum shear strain rate. They actually nucleate in areas that are a low strain rate that is adjacent to an area that's at a high shear strain rate. They don't require general shear, so all our models were simple shear, although I'd like to repeat this under pure shear and see what happens. They don't form at the last stage of shear zone activity. They start forming really early on in these models and continue forming throughout the duration of the model, and they only require 5% weak phase to form, as I mentioned earlier. Okay, so that's a quick overview of this paper, and if you have any questions about that, you can contact me via email, or you can also read the paper. It's available from my website, melaniefinch.net, or on ResearchGate, and you can also see the movies on YouTube, but links to all of that is available on my website. Thank you very much for watching this seminar, and I hope to speak to you soon. Bye.